Hi friends, welcome to Civilianz. In this session we are going to talk about the signal design by Webster's method, which is one of the very important topics from the GATE examination point of view. If you are looking at the previous year's questions came from this transportation engineering subject, which is having a weightage of around 10 to 15 marks in every year. Around 3 to 4 marks will be definitely from traffic engineering chapter, right? And in that there is high probability that the questions will be coming from this particular topic. See, not only for the GATE examination but also for other exams in which transportation engineering is a part of the syllabus, then this is actually one of the very important topics. So I hope this session will be very helpful for you for your upcoming exams. Okay, so coming to the topic, signal design by Webster's method. We'll come back to this Webster's method. First of all, let's focus on this signal design. It's something which is very familiar to us, right, in our day-to-day life. We all used to travel a lot, and this signal designs or these signals are very familiar to us, right? In which order we'll be seeing these signals? Definitely they are not going to put all these signals together, right? It will be coming one by one. So in which order you are going to get this signal? Yes, of course, first of all, we'll be having this green signal. That is the order in which they are going to show the signals, right? Then after that, whenever you are seeing the green signal, definitely you will be moving in your vehicle, and suddenly you will be seeing the yellow signal, right? We will not be calling it as yellow, we will call it as, there you go, amber signal, right? A-M-B-E-R, amber. So after green, we will be having the amber, then we will be having the red signal. This will be the order, right? So whenever we are getting the amber signal, or you are just about to reach that the intersection and you are seeing the amber signal, what you will do? Actually, we have to reduce the speed and stop, right? But sometimes we may be accelerating and going also, right? That should not be happening, no? But we'll do that. Yes, that is also a purpose of amber actually. Actually, the amber signal is provided for two reasons. One is, suppose you are, you have not reached at the intersection, you are just somewhat far away, and you are seeing the amber signal, then what you need to do? As we have told earlier, we need to apply the brakes and decelerate. We need to stop the vehicle before the intersection, right? That is what generally comes in our mind. Also, suppose if you have already reached at the intersection and it is not possible to apply a sudden brake and stop your vehicle, right? If you are applying sudden brake, definitely, some vehicles will be following you. They will be coming and hitting on your backside, right? Okay, backside of your vehicle, right? So what we need to do? Suppose if it is unable to stop your vehicle within that amber time, then you need to accelerate and clear off the intersection. So for both these purpose, they are providing the amber signal. Okay, so generally for 2 to 4 seconds they may be giving that. And after the amber signal, we will be having the red signal, and for around 30-40 seconds, depends upon the traffic, we need to stop your vehicle. Then after the red signal, again we will be having the green signal. Again we will be start moving, right? So this is the order. Order is also important for 1 mark kind of questions. So first green, then amber, then red. But can we say it is first green? No, right? It's a signal cycle. There is no starting point of a cycle, right? That's why it is called as a cycle. Which means if I am taking the beginning of the signal as the amber, I can say amber to amber, whatever is the duration, same duration will be getting from a red to the next red. The same duration will be having from a green to the next green. All these are same, right? Okay, so which means if I am representing the signal cycle like this, just a second. Suppose like this, a rectangle I am drawing, and if I am having the red signal for, let's say, the red signal I am having for around 40 seconds, okay? So red is for 40 seconds. So after red, I will be having the green signal. I'm just drawing it here. So after that, I'll be having the green signal. Let it be, that is for 30 seconds, let it be, okay? And after that, we'll be having the amber signal also. Amber signal, I'm just putting A, okay, for your information, it is A-M-B-E-R. We will not call it as yellow as I told you before. It is amber, okay? So let's say amber is 2 seconds. Now, after amber, again we'll be having the red signal. We can just draw it here also, but not required. So just like this, we will be drawing a rectangle which is showing the corresponding time of each signal, which means how much will be the red signal, how much will be green, how much will be amber, like that. It's not necessary to show red initially. We can start from green also, which means green 30 seconds, then amber, then red. Like that also we can draw. Similarly, amber, then red, then green. Like that also we can draw. But this is the general way used to represent it. Why? Because in a signal cycle, see, let's take an example of a clock. Okay, a clock is actually a cycle, right? Which means 1 AM to 1 AM, if you are taking, you will be getting 24 hours. 2 AM to 2 AM is also 24 hours. 5 o'clock to means 5 AM to 5 AM also 24 hours. 9 PM to 9 PM, that is also 24 hours, right? So everything is 24 hours, right? But for our convenience, what we'll do? We'll consider the 12 AM as the starting of that time, or starting of the day, or starting of that 24 hours, right? For our convenience, we are taking it. Whichever point or whichever time you are considering as the starting point, still you will be getting 24 hours only, right? For our convenience, we are taking 12 AM as the reference. Similarly, for a cycle, so a signal cycle, we will be considering the beginning of the red signal as the starting of a cycle. Understood? Which means this cycle will be having how much duration? 40 seconds plus 30 seconds plus 2 seconds, totally it will be 72 seconds, no? So if I am taking the beginning of the green signal as a reference, then to the next green, what will be the duration? 30 plus 2 plus 40, still 72 only. Or if I am taking starting of the amber as my starting of the signal, then also it will be 2 plus 40 plus 30, then also 72. So whichever point you are considering as the starting point of the signal cycle, still the cycle length will be same, or the duration of the cycle will be same. But for our convenience, what you are doing, we are considering the starting of the red signal as the starting of a cycle. So we can represent, see like this, from here to here will be the duration of a signal cycle. We can call it as cycle length. We can call it as cycle length. Okay, cycle length or cycle time, sorry. Cycle length or cycle time, anything we can call. Okay, so how can we define the cycle length? This is also important for 1 mark questions. Beginning of a red signal to the beginning of the next red signal, or we can say end of the amber signal, right? After amber signal is ending, then we'll be having the next red, right? So from the beginning of a red signal to the beginning of the next red signal will be one cycle, or the duration of that cycle we can call it as cycle length. Got it? Now how much we need to provide a signal cycle length? That is also important. Suppose if the cycle length is very less, which means suppose say, let's say instead of this 30 seconds, we are providing only 10 seconds. So what is the problem then? Suppose you are there in the signal and you are getting the green signal, you may be around the 10th or 11th vehicle in the queue. You are getting the green signal there, okay, you will be starting your vehicle, you will start moving, putting in the first gear slowly, you may be putting in the second gear. By the time you are reaching at the intersection, again you will be getting the maybe amber and red again. Again you need to turn off your vehicle, and whenever you are getting the green signal for the next time, again you need to restart it, start your vehicle and again moving, right? You might have experienced this, right? If the traffic is huge and you are in the queue, maybe in the back side, okay, maybe 11th or 12th or 15th vehicle, then whenever you are getting the green signal, sometimes you may not be getting chance to cross the intersection, right? By the time you are reaching at the intersection, again it will be coming as red. So sometimes such problems may happen, right? When it will be happening? If the green signal is so less that you will not be getting enough time to clear off the intersection, right or not? So if the cycle length is very less, what is the problem? The delay will be increasing. You will not be able to cross the intersection fast. You will take more time. So delay will be too much, right or not? Okay. So if I am just taking a graph, let's see here. If I am simply considering a graph in which I am taking the delay on the y-axis. What delay? The average delay of vehicles on the y-axis. Average delay of vehicles on y-axis, and here I am having the cycle time or cycle length. Cycle length or cycle time, like that also we can call, okay? It's definitely it will be in seconds, right? So cycle length or cycle time. Let's see what we have discussed now. If the cycle length is very less, obviously the delay will be too much, right? And as the cycle length increases, we are giving more time for the vehicles to pass. Definitely delay will be decreasing or not? Of course. But what if we are giving too much time for a particular lane? See, when you are getting the opportunity to move, which means you are there in the signal, just assume that you are there in the signal, you are getting the green signal and okay, you are moving, right? It's well and good. Average delay will be decreasing. But what about the other vehicles? They will be waiting for their chance, no? Right or not? If you are there at the intersection and if you are getting green signal, which means there will be some other roads on which vehicles will be stopping and waiting for their chance. They will be having red signal there, right or not? So we shouldn't be giving too much cycle length for a particular road because other vehicles will be getting affected then. Understood or not? Okay. So if the cycle length is too much, then obviously this delay will slowly start increasing. Understood? So if the cycle length is very less, then also average delay is too much. If the cycle length is more, then also average delay is too much. And why this delay is increasing again? Because if you are getting green signal, other vehicles will be having red signal only. So if you are considering what? The average delay, not the delay of a particular vehicle. We are not talking about a particular vehicle, right? We are talking about the average delay because a signal has to be designed for every vehicles which are coming on the intersection. We are not designing the signal only for one particular road, right? We are designing it for all the roads which are coming and meeting at that intersection. Understood or not? So this value, this particular value, what is this point? This point is optimum point. This is the point which is representing the least value of the y-axis. What is y-axis? Average delay per vehicle. Okay. So this value is the least value of average delay per vehicle, right? Average delay per vehicle. Now corresponding to this, we will be having a value on the x-axis or not? What is that? This will be the optimum value of the x-axis. What is there on the x-axis? The cycle length. So this particular value, we can call it as optimum cycle length or optimum cycle time. Anything we can call. Optimum cycle length or optimum cycle time. So if I am just representing cycle time as C, this is optimum. So CO, like that, what we are generally used to represent. CO, optimum cycle length. So what is the meaning of that? If the duration of the signal cycle is less than this CO value, optimum cycle length, obviously delay will be increasing. Similarly, if the signal cycle length is more than this optimum value, then also delay will be higher. So what is our intention? We have to find this optimum cycle length value, and whatever we are getting that value, let it be 70 seconds or 80 seconds or 64 seconds, whatever it is. That value, if we are splitting into 3, which are red, green and amber, if we are providing that particular duration on the intersection, then the average delay per vehicle will be least. So that's what we need to give, no? To give equal opportunities to all the vehicles which are coming at the intersection. This value we need to find out first, and that value we are going to provide for the signal. What is the meaning of that? Whatever is this C0 that we are going to find out, that should be equal to this red plus green plus amber. So this value we have just put as example initially, right? So we don't know how much it is. We are going to calculate it. Okay. Only thing we know is the red duration plus green duration plus amber duration should be equal to our optimum cycle length value. Then only we can ensure that the average delay per vehicles which are coming at the intersection will be the least value. Got the point? Now what is our intention now? We need to calculate how much will be this C0 value at which the average delay per vehicle will be least. Okay, so to find this CO value, we are having lots of methods. Okay, many traffic engineers came forward with the different equations, and finally IRC, the Indian Road Congress, has accepted the design given by the traffic engineer Webster. That's why we are studying the signal design by Webster's method. It's an empirical equation. We need to by heart that equation. There is no proof for that equations and all. Okay, that's what we call it as empirical equation. And the empirical equation given by Webster got accepted by IRC. We know IRC gives the various standard rules and specifications regarding road designs, right? So IRC has accepted Webster's method. So we need to study that. But IRC has given some, what I can say, some specifications and all. Suppose in Webster's method, if something is not available, then we can do this. If something is happening like that, then you go for this, like that. specifications IRC has given that I will be explaining when we are discussing some questions and all. Okay, so first of all, let's see what Webster has given us. According to Webster, the optimum cycle time CO is equal to 1.5 L plus 5 whole divided by 1 minus capital Y. So this is our equation. This we need to by heart. CO is equal to 1.5 L plus 5 divided by 1 minus Y. Now look at this equation. There are two unknowns here, right? This L, this capital L, and this Y, right? And the remaining things you see, 1.5, it's a constant, and you need to remember that will be a constant value, okay? It will not be changing with respect to question data. And plus 5, this 5 is also a constant value. 1.5, L will be varying, plus 5, it's a fixed value, whatever be the question data, this will be fixed value, divided by 1 minus capital Y. So this L and Y are the variables here, okay? From signal to signal, this L and Y will be varying. Now what is this L and Y? This L is nothing but the lost time per cycle. What is the total lost time or the time that we lost in a signal cycle? That is called as capital L, that what we denote by capital L. And Y is nothing but the sum of critical flow ratios. Sum of critical flow ratios. Now what is the meaning of this critical flow ratio then? As the name indicates, these are some ratios, and the ratios that we need to add, right? Sum of critical flow ratios it is. So if I am just denoting the critical flow ratio as some small y, let it be, then can I write this is equal to some y1 plus y2 plus y3 plus etc. some yn, we don't know. If you are having n number of critical flow ratios, I am just going to add all of them. That's why we have written as sum of critical flow ratios. Got it? Now we don't know what is the meaning of this critical flow ratio, that we are going to find out. Okay, let it be there as of now. Okay, so at least you have understood what is L and what is capital Y, right? So let it be there. Let me just take a simple question first of all, then I will come back to that capital Y. Okay, so look at this question. Ask for the gate examination for 1 mark. In a signal design, if the sum of ratios of normal flows to saturation flow, what is that? That is what is actually the critical flow ratio. Okay, let me just write that also here. Okay, so each of this critical flow ratio indicates, it is equal to the normal flow to saturation flow. And I will explain what is this normal flow and saturation flow. Okay, so normal flow to saturation flow. This ratio is called as the critical flow ratio. Now from where this critical flow name came? This normal flow is also called as critical flow. This normal flow is also called as critical flow. So which means the critical flow ratio can also be defined as the ratio of critical flow to saturation flow. That's why it is called as the critical flow ratio, and always this ratio will be less than 1. That is also an important point for 1 mark, which means all these y1, y2, y3, y4, etc. all these ratios will be less than 1, like 0.1, 0.2, 0.15, 0.22, something like that you may be getting. Okay, all these will be very less values. Okay, now again if you are going back to the question, if the sum of ratios of normal flows to saturation flow, what is the meaning of that? The capital Y value, right? Is 0.5, which means how many small y values will be having here? We don't know as of now, right? Because they have directly given the capital Y value, right? Sometimes they will be giving different small y values. We need to add it and find this capital Y, or sometimes directly they will be giving the sum value itself, capital Y itself they will be giving. So look at this particular question, whether they have given different ratios. No, they have given the sum directly, right? How much it is? 0.5. Okay, and the total lost time per cycle is 10 seconds. The optimum cycle length in seconds will be, how to calculate it? Very simple, 1.5 into L is how much? 10 seconds. 1.5 L plus 5 whole divided by 1 minus capital Y is 0.5. This is nothing but our optimum cycle time. How much it will be? 15 plus 5, 20. 20 divided by 0.5. Very simple question. 40 seconds. Right or not? 40 seconds. Got it or not? So which option will be right? Option D will be the correct answer. Simple question. Now what is the next level? Instead of giving this 0.5, they will be giving you the different values. For example, let's say here we are having two different values of ratios, y1 and y2. Instead of giving this 0.5, they could also given like this: y1 is equal to 0.3, y2 is equal to 0.2. Suppose if they are giving like that, or the critical flow ratios at the signals are 0.3 and 0.2. Then also what we are going to do? Then to substitute in the equation, we will be adding these two. We are going to get 0.5, then we are going to substitute it here. Understood? Like this also they could have given, but directly they have given 0.5. That's it. Understood, guys? Simple, no? Yes. Now, going into the next question, letter B there, we are going to explain the concept through questions, okay? Look at the question. A signalized intersection operates in two phases, okay? The loss time is 3 seconds per phase. The maximum ratio of approach flow to saturation flow. What are these? These are the synonyms for the normal flow. Approach flow is also called as the normal flow or critical flow, okay? So there are three names: normal flow, critical flow and approach flow. All these three are same. Now saturation flow already we have seen. For the two phases are, see, look at here, this is what I told you, 0.37 and 0.4, which means what? y1 is equal to 0.37 and y2 is equal to 0.4, which means the capital Y value will be how much? 0.37 plus 0.4, 0.77. We got it. Okay, let it be there. But this is not the question. What is the question? The optimum cycle length using Webster's method. Okay. Now, CO is equal to 1.5 into, how much is L value? 3 seconds, 1.5 L plus 5 divided by 1 minus Y. How much is capital Y? 0.77. We have already calculated, right? So here you are going to get a beautiful value, but that will be absolutely wrong. Why? This is the trap, one of the traps which used to come in traffic engineering from Webster's method. Look at here, there is an important point to be noted here. Look at this question. Why it is wrong? Because we have substituted a wrong value of L here. This is actually not 3. Why? Can anyone find that? Hope you got it. What is that? They have mentioned that the lost time is 3 seconds per phase. So what we have written, the definition of L, going back, the definition of L, see, look at here, the lost time per cycle, right? But in that question they have given the lost time per, not cycle, they have given lost time per phase. These two are different. Then what is the difference between a phase and a signal cycle? Let's discuss that. Then we have to come back to this question and what I can say, correct this value 3. Okay, so let's see this. Let's say this. So let's say you are there in this car. Okay, you will be waiting for your chance to move, obviously, right? So look at here. If you are having a red signal here somewhere, see here you are having a red signal. Obviously other vehicles will be moving, no? So these vehicles will be moving like this, and obviously definitely if you are having this red signal, maybe they will be also having a red signal, and these people also will be having a red signal. That is why they are moving, right? And these people can also move, see, in this direction. They can also move in this direction, right? And after some time, this particular road will be getting the red signal, and maybe another one will start move. Okay, this will be going face to face, right? Stage to stage. If I am taking another example, like a top view, this is how generally we represent. Okay, so let's say this particular road is having the green signal. So they will be moving straight. They can go left. They can take the right turn also. This is what is happening in one stage. So obviously all the other roads will be having the red signal, right? So you will be a red signal. So all the vehicles will be stopping here. Another red signal. All the vehicles will be in queue. So this is what is happening in one stage. And in the other stage, what will happen? The next road will be getting the green signal. Let it be here they are getting the green signal. So whichever vehicles coming in this direction, they can go straight. They can take the left turn. They can take the right turn, no issue. Why? Because the other vehicles will be getting the red signal. So here still they are in the queue, they are waiting for the chance. So these roads, these vehicles are also there still in the queue. Okay. So similarly, the next stage, in the third stage, this road may be getting the chance. So the vehicles which are coming in this direction can take the left turn, can take the right turn, no issue. Now this road will be definitely having the red signal, right? So these roads will be having the red signal. So these things we know already, right? Okay, now let's just draw one more. Now these vehicles, they were waiting for so long. Now these vehicles are also getting the chance to move right turn, left turn, straight, whatever. And these will be having the red signal and they will be in queue. Now tell me, what is going to happen next? Now we have already drawn 4 stages, right? This was stage 1, this was stage 2, this was stage 3, and this was stage 4. And after stage 4, what will happen? Again, it is going to happen like this, right or not? So how many stages we have taken to give chance to all the vehicles to move? 4 stages, right or not? What about the 5th stage? That is same as the first one, right or not? So in this signal cycle, we are having 4 stages. These stages we can call as phases. So this is phase 1, and this is phase 2, and this is phase 3, and the last one is phase 4. See, there is no order, okay? So which means it is not mandatory that the phase 1 should be always from left to right. Nothing like that. Anything we can consider as a phase 1. Simply the phase indicates, a phase in a signal indicates it's a stage, that's it. So if I am telling that it is a 2-phase signal, which means there will be 2 stages. What about this particular signal? This signal I can call as it is a 4-phase signal. It is a 4-phase signal, or I can call it's a 4-phase signalized intersection. Like that also we can say. It is a 4-phase signal, or we can say it's a 4-phase signalized intersection. So whenever we hear there is a 4-phase signalized intersection, what we need to understand? Okay, then in that particular intersection, there will be 4 stages. There will be 4 phases in which all the vehicles which are coming at that intersection will be getting a chance to move. Understood? Or we can say that intersection design operates in 4 different stages or 4 different phases. So this is an example of a 4-phase signal. Okay, but in our question, look at this question. Going back to the question, what they told, it operates in 2 phases. How it is possible? In 2 phases, is it possible to give chances to all the vehicles just in 2 stages? Which means the first stage and the third stage should be then same. Then only it will be 2-phase signal, right? Is it possible? What do you think? Let's take an example. Let's check it. Suppose this is having a red signal. This is also having a red signal. Okay. Now, whichever vehicles are coming, they are going to stop in the queue. And I am telling, here we are having the green signal as we have mentioned before. Okay, the vehicles are going like this. Here also we are having the green signal. Then what will happen? The vehicles which are coming will go like this. Then it is not possible for a vehicle to turn like this to the right side. That is not possible. But whether they can go left, yes, there is no problem, right? Whether these vehicles can go left, yes, there is no problem, right? But is it possible for the vehicles coming in this direction to take a right turn? No, because conflict will come here, right or not? Which means if we are not allowing the vehicles to take the right turn, then 2 roads can travel together, or the vehicles which are coming in 2 different roads can travel simultaneously. That is possible. But only condition is we should not be allowing them to take the right turn. Then what to do? If someone wants to go to right, what to do? First they have to go left. Maybe somewhere here they have to take the U-turn. Then they have to come like this. Right? That is the traffic regulation that may be adopting there. Understood? And after some time what will happen? For these roads we are going to give the red signal. So these vehicles now they have to stop here. So all these are representation of queue. Okay. Fine. Now the other roads in which vehicles were waiting previously, now for these 2 roads what we are doing? We are giving the green signal. Now they can go straight, no problem. They can go straight, there will not be any accident. they can also take the left turn. Okay, they can also take the left turn, no issue. Whether they can take the right turn? No. Then vehicle will collide here. Accident will happen definitely. Understood or not? Now, happened. Two phases has been over now. So here it is phase 1. Here it is phase 2. Now what about phase 3 now? Phase 3 will be same as phase 1. Understood or not? So whether we will be having two more diagrams here? No, this is it. This is the end of the signal. That's it. So this signal we can call it as it's a two-phase signal, or it's a two-phase signalized intersection. It's a two-phase signal or two-phase signalized intersection. Understood? So two-phase is also possible. So we have seen 4 phases, we have seen 2 phases. Now is it possible to have a 3-phase signal? Of course yes. How? In one of the road, if you are allowing the right turn, means here we are not allowing the right turn. Now in one road we are going to allow the right turn, then it will be a 3-phase signal. Means in both roads, if you are allowing right turns, like in the previous question, the previous diagram, right? In all the roads we are allowing right turning also, right? They are turning left, they are turning right also. In that case it will be 4. Now in one of the roads, if you are not allowing the right turn, then 1 is eliminated. So it will be 3-phase signal. Now in both the roads, if you are not allowing right turn, 1 is eliminated, the other right turn is also eliminated. Now it will be 2-phase signal. Like that also they can ask a question. Understood? So both roads, on both roads, if you are allowing right turning, then it will be 4-phase signal. In one of the roads, you are prohibiting the right turn, then it is a 3-phase signal. In both roads, in one of the roads, if you are prohibiting right turn, then 3-phase signal. In both roads, if you are prohibiting right turn, then it's going to be a 2-phase signal. That's what we have just drawn here. Understood or not? Okay. Now you got the concept of phase and a signal, right? Now coming back to this question. The lost time is 3 seconds per phase. Total how many phases are there? 2 phases, which means the last figure which we have drawn, right? So in one phase, or the first phase, we are having a loss of 3 seconds. In the second phase also, how much will be having? Again 3 seconds. What they told is 3 seconds per phase. So in a 2-phase signal, or in a signal which operates in 2 phases, how many phases will be there? 2. That's why we are calling it as 2-phase, right? So there will be 2. In each phase, how many seconds are getting lost? 3 seconds. So totally capital L will be how much? There you go. It will be 6 seconds. Why? In the phase 1, we are having 3 seconds loss, and in phase 2, again we are having 3 seconds loss. So totally in the cycle, capital L is going to be 6 seconds. Understood, guys? Okay. Now substitute there. So substitute there. What will your value then? The C0 is going to be 1.5 into 6 plus 5 divided by 1 minus 0.77. Understood or not? Now once you are doing this, we are going to get a value. Let me just calculate it. Yes, 60.87 seconds. Got it? Now in the question they have mentioned that to round off to 1 decimal place, right? So round off to 1 decimal place means we can round off to 60.9 seconds. That's it. 60.9 or 60.8, anything you can substitute, doesn't matter. Got it, guys? So these are the twists which may be coming in the calculations. Okay, shall we go to the next question then? We can discuss all the varieties of questions which are coming in this particular topic. Now look at here. Simply another question. It's a 3-phase signal, which means what? Phase 1, phase 2, phase 3. Simple. Okay. So that before reading the question, you please tell me how many small y's will be having, which means the normal flow to critical flow ratios. How many ratios will be having? For each phase, we can calculate small y values. Okay. In the second question also we have seen 2 phases like that. So each phase will be having each critical flow ratio, which means y1, y2, y3 like that. Which means if you are having 3 phases, how many small y's you are going to have? You will be having 3 values, y1, y2, y3, because it is 3 phases. Understood, guys? Okay. Oh, just a second. Okay. Now that value is what they have given, 0.3, 0.3 and 0.2. So y1 is nothing but 0.3, y2 is nothing but that is also 0.3, y3 is equal to 0.2. which means how much will be capital Y then? 0.3 plus 0.3 plus 0.2, 0.8. Got it? Right. And this capital Y also will be less than 1 always, okay? So that you can keep in mind. Small y is also less than 1, and their sum, capital Y, is also going to be less than 1 only, definitely. Okay? So 1.5 into, how much is capital L? Last time is 3 seconds. Are we going to substitute 3 here? No. I hope you might have already noted down that. Last time per phase is given here as well, right? How many phases are there? 3 phases are there. So in each phase we are having 3 seconds lost, right? So like this we are having 3 phases. So totally L will be 9 seconds. That's it. Okay. So hope you have noted that already. So 1.5 into 9 plus 5 divided by 1 minus, here we have already calculated capital Y, 0.8. So once you are doing this calculation, let me just check it. Yeah, you are going to get 92.5 seconds. Hope you got the right answer. Okay, so here they have not mentioned, okay, so it's not a gate question, that's why I have not written there like 1 decimal, 2 decimal like that. If they are asking us to round off to integer, then we can round off to 92 or 93, anything is fine. Or if it is 1 decimal, then 92.5 like that. Hope you got the concept, right? Now let me just go into somewhat detail. Look at here. So all these questions, in all these questions, they have given directly what is the ratio, right? 0.3, 0.2, in previous question 0.4, something like that they have given. How we are going to get these ratios? That is the next thing. Already we have mentioned that it is the ratio of the normal flow to saturation flow. Okay, so look at this data. From this data, what you are understanding, this phase will be, or this signal will be how many phases? Operates in how many phases? There you go, 3 phases, right? That's why they have given first phase, second phase, third phase. Okay, if you are having a 3-phase signal, then obviously we will be having these 3 phases. In each phase, they are given normal flow, saturation flow, normal flow, saturation flow, so on. Which means for the first phase, for P1, how much will be the Y value, or I can call it as Y1? The normal flow to saturation flow of that first phase. So how much it will be? 680 divided by 3100. How much will be then for P2? For phase 2, how much will be Y2? 660 divided by 2800. Now for phase 3, how much will be the critical flow ratio? I can call it as Y3. Critical flow ratio will be 720 divided by 2800. We got all the small y values. Okay, let me just calculate it. How much it will be? The first value 600 by, just a second, it's 680, right? Okay, let me just calculate it. I don't have the data right now. Okay, just a second guys. 680 divided by 3100. We are going to get it as 0.219. Okay, so similarly this is 660 divided by 2800. It's going to be 0.235. Okay, we can take more decimals for more accurate final answers. So at least to take 3 decimals, okay, every time. So this 720 divided by 2800, it's going to be 0.257. Okay, so these are the values we are having. Now what we can do? We can just add all these 3 values, 0.219, 0.235, 0.257. Just add all those things. We are going to get your capital Y value. Right or not? Yes. Now look at the data again. The normal flow and saturation flow values measured at a 3-phase signalized intersection is as given below. Okay, we have calculated the capital Y also. Just add all these 3. If the altered time for the signal is 6 seconds, optimum cycle length will be, let it be there. How to calculate the optimum cycle length? C naught is equal to 1.5 L plus 5 divided by 1 minus Y. Now this capital Y we can calculate. How? We just have to add all these things. Okay, so that is over now. Okay, we can do that. That is over. Now what is the unknown here? Capital L is unknown. But here they have given another data. What is that? Already time is 6 seconds. So can we put 6 here instead of this L? No. What is capital L? Capital L is the lost time per cycle. It is not the altered time, right? Then what is this altered time? Then what is the use of that given data in this particular context? That is what is IRC is telling. I told you in the starting, right? Whenever we are adopting Webster's signal, IRC has given some suggestions. What are those suggestions? One of the suggestion is, if the capital L value or the lost time per cycle is not available, what we can do? This L we can take as 2n plus r. Okay, what is this 2n plus r then? What is 2n plus r? This n is nothing but the number of phases. N is nothing but the number of phases, which means if it is a 4-phase signalized intersection, n equal to 4. If it is a 2-phase signal, n equal to 2. If it is a 3-phase signal, in this question it was 3-phase signal, right? Then n equal to 3. Then what is this r? You might have already understood that this is nothing but the all-rudder time. Okay, this r is nothing but the all-rudder time. So in this particular question, then how much will be L then? If you are substituting, L is equal to 2 into the number of phases were 3 plus all-rudder time is given as 6 seconds, right? So 2 into 3, 6 plus 6, it's going to be 12 seconds. That's it. Got it, guys? So go back to the question and substitute there. So our C0 is going to be 1.5 into 6 seconds plus 5 divided by 1 minus capital Y. Capital Y I don't have the value right now. That's why I am not writing. How to calculate capital Y? Just add all these 3. That's it, simple. Okay. I am requesting you to just answer this particular value in the comment box. Okay. So that we can confirm whether you have understood the concept or not. I will also understand whether this section got helpful for you or not. Okay. So I am requesting you to substitute this, comment this particular answer in the comment box once you are watching the video. Alright, guys. Now let me just discuss one more thing here. We have simply written all-rudder time, right? Now what is the meaning of this all-rudder time? That also we need to discuss now. Then only the concept will be 100% clear. If I am going back to that particular figure, okay, let me just take this. Okay. Now leave the first part. We have already discussed that. Let me just take this particular intersection. Okay. Let me just focus on this. Now, is there any situation? I'm just drawing a signal cycle here, or simply a signal situation here. Look at here. There is a red signal in this road, means all the vehicles which are coming in that road is stopping their vehicle. Red signal here also, which means here also there is a queue. Red signal here as well, there is a queue. Red signal here also, there is a queue. Will there be any situation like this? No, right? See, look at this. Look at this figure. Look at this figure, or look at the previous figure. At least on one of the roads will be having the green. 3 will be red and the other one will be green, obviously, right? Look at here also. At least one road or more than one road definitely will be having green, right? Will there be any road like this? All the roads are having red signal. Array, what is the purpose of that? All the vehicles are stopping. What is the purpose? There you go for pedestrian traffic, exactly. Okay, so pedestrian traffic, we can keep the signal like this, so that if anyone want to cross the intersection from here to here, or from here to here, or from here to here, can easily cross the intersection, right or not? So this is what we call as all-rudder time. All are having red. See, not only for pedestrian crossing, but also sometimes what may happen in some intersections, all the vehicles may not be able to cross properly, right? Suppose here, some vehicles maybe they are new to the road, they are not that much experienced in driving, and sometimes they may not be able to cross the intersection in the exact time. Maybe in the amber time and all, they may not be able to accelerate like other vehicles because they may be having fear, no? They are not that much experienced. So it will be slowly only they may be crossing the intersection, right? So suddenly if you are giving the green to the other road, they will also be coming fast. So there may be a chance of collision, right? So such vehicles which got trapped in the intersection, to clear off such a trapped vehicles in the intersection, then also it will be helpful if we are providing a signal like this. If any vehicle is there inside the intersection, then they can clear off fast. Okay, so this is actually called as the all-rudder time. As the name indicates, all are red. That is the meaning of all-rudder time. Got it, guys? So these are the important concepts related to the traffic signal design. So I hope you understood all the concepts. And one more thing, let me say, we have taken the ratio of normal flow to saturation flow, no? So what is the difference between normal flow and saturation flow? Let me tell you that as well. That also sometimes can be asked for 1 mark. Normal flow means as the name indicates, the actual flow which we are measuring. In normal condition, what is the flow there? Flow means what? The vehicles which are coming in 1 hour. Okay, so that is the meaning of the normal flow. Under normal condition, when the vehicles are traveling on the intersection, we are just counting them. So in 1 hour, how many number of vehicles has been came? So that is called as the normal flow. Then saturation flow means, suppose if we are not providing any traffic signal there, then the vehicles will not be coming and stopping there. Now they will be continuously going. It's an ideal situation. In an intersection, if we are giving 1 hour green signal, okay, let me explain again. In the traffic signal design or for any particular road, if you are giving an ideal situation, 1 hour continuously you are giving green signal, then in that 1 hour, whether they have to stop the vehicle, not required. They will be continuously going. Now, will that be happening in an intersection? No, 1 hour can we give green signal to any particular road? No, it's not possible. That's why I told you that it's an ideal situation. So in 1 hour, if you are giving green signal continuously for any particular road, then what will be that particular number of vehicles which can cross the intersection? Or in other words, if you are not at all providing any signal and there is only one particular road, there is no other road or there is no intersection, then vehicles will be continuously moving in 1 hour. Then that particular value, that will be a huge number definitely. Okay, that value is called as saturation flow. But that is not going to happen practically. In between, we are going to give red signal. So vehicles will be definitely interrupted. They have to come and stop, then again they have to start and go. So the number will be decreasing. So that value is called as the normal flow. So obviously normal flow to saturation flow ratio will be less than 1 obviously. Because saturation flow is an ideal concept. Without having any interruption, what can be the maximum number of vehicles that can go in 1 hour? Definitely higher than normal flow, no? Yes. That's why I told you small y values will be always less than 1. Get the concept now? That's it. Okay. So that's it. That's the end of this particular session. I hope the session got helpful for you. And whatever the number of or whatever be the level of question they are asking in the GATE exam, I hope you will be able to crack it easily. Okay. So if you have liked the video, please show your love in the form of likes and comments in the chat box. Thank you so much.
Start your preparations for engineering competitive exams from top educators. Learn from the best.